Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Fouling in heat exchangers, economic impact, sizing impact, and mitigation strategies. In this video course, you will learn what is the economic impact of fouling, how does the fouling increase the size of the heat exchanger, strategies to mitigate fouling by design approaches, strategies to mitigate fouling in heat exchanger operation. Please subscribe to the channel. By subscribing, you will motivate us to produce knowledgeable video content for you. So please subscribe now before you forget. Fouling in heat exchangers is one of the major problems in refineries, petrochemical plants, and other chemical process industries. It is considered as the main source of energy loss, accounting for a significant portion of the refinery's total energy consumption. Fouling of refinery process heat exchangers can cause significant economic penalties. As fouling formation occurs, the heat transfer capacity of the exchanger decreases, increasing the external energy demand to provide the required heat to the process. It may be that higher heat load is required in the furnace, which leads to more fuel consumption in the furnace. The amount of greenhouse gas emission increases. In many petrochemical plants, the hot reactor product stream at temperatures as high as 500 to 550 degrees centigrade is used to preheat the feed stream. In these plants, the preheat temperature of the process stream may drop due to fouling to such a value that the operation is not sustainable, forcing the unit to shut down with considerable loss of production. Hence, it is extremely important to give attention to the aspect of fouling in the heat exchangers. Illustrated in this figure is a reactor train in a petrochemical plant consisting of a reactor and a series of heat exchangers downstream of the reactor for heat recovery and feed preheat. Fouling of the heat exchangers affect the heat recovery and reduce the preheat temperature of the feed to the reactor, which significantly impacts the reactor performance. The economic impact is contributed by several factors that include energy cost, maintenance cost, production loss due to reduced throughput. The energy cost is typically the cost of additional fuel required in the furnace to maintain the process temperature. Throughput decrease is necessitated by increased fouling on the heat transfer surface, which causes higher pressure drop in the process loop. Maintenance cost is the cost required to clean the heat exchanger by shutting down the plant. Many heat exchangers fail without warning due to under-deposit corrosion. The user has to face unscheduled plant shutdown for heat exchanger cleaning, firefight, and spend sleepless nights to take corrective action with enormous loss of production and profit. In certain instances, the heat exchanger tube material has to be replaced with more compatible MOC such as graphite, which calls for additional capital cost. Fouling occurs in all types of heat exchanger services: gas to gas, gas to liquid, and liquid to liquid. Most of the fouling research in the industry has been restricted to liquid side fouling, particularly for fouling in water-cooled heat exchangers. Gas side fouling is experienced in fired heaters, furnaces, and boilers in the heat recovery sections. The consequence of gas side fouling is loss of heat recovery and failing of tubes due to corrosion. In several fuel oil fired packaged boiler units, Boiler efficiency is improved by use of economizers, which preheat the boiler feed water. In such heat exchanger, tubes have prematurely failed. Thus, it is apparent that fouling is a problem that has considerable impact in heat exchanger performance and contribute to increases in energy cost and maintenance cost. How does the process designer take into account the fouling phenomena at the stage of designing heat exchangers? What is the approach to handle fouling during operation of the plants when the heat exchanger performance is negatively impacted by fouling? Let us move on to find out. Impact of fouling on heat exchanger size. Fouling is defined as the formation of deposits on the heat transfer surfaces, which affects the heat transfer rate and the flow through or across the tubes. The fouling layer has high thermal resistance to heat transfer. This figure illustrates the fouling formation on a heat transfer surface as the fouling fluid flows through the tube and the heat transfer takes place across the tube wall. The fouling layer formation consists of deposition of solid on the surface accompanied by removal of some of the particles already deposited by erosion, etc. The fouling layer formed grows in thickness when there is a net increase in deposition. This figure illustrates a typical fouling resistance variation with time for an industrial heat exchanger. The shape of the curve depends on the heat transfer process and the mechanism of fouling that progresses on the heat transfer surface. Three curves are shown. Curve A is a linear relationship, meaning the rate of increase of fouling resistance is constant with time. This behavior is observed with hard deposits, which is usually observed in heat recovery exchangers in petrochemical plants due to coke formation in high temperature reaction of light hydrocarbons such as olefins. Curve B reflects the fouling behavior of deposits formed by precipitation of weak deposits in water system. The curve C exhibits asymptotic behavior, where the deposit formation after the initial increase stabilizes when the deposit formation equals the deposit removal. This is typical of weak particulate fouling layer of low strength. In the absence of fouling layer, the overall clean heat transfer coefficient based on the outside area of the tube is expressed as 1 by capital UC equal to 1 by HO plus DO into L and DO by DI divided by 2 times KW plus DO by DI times 1 by HI. The overall dirt heat transfer coefficient is expressed as 1 by capital UD equal to 1 by HO plus 1 by HOD plus DO into L and DO by DI divided by 2 KW plus DO by DI times 1 by HID plus DO by DI times 1 by HI. Where UC is a clean overall heat transfer coefficient, UD is a dirt overall heat transfer coefficient, Kw is a thermal conductivity of the tube wall. The subscripts I and O refers to the inside and outside of the tubes. Di is the inside diameter of the tube. Do is the outside diameter of the tube. HID is a tube inside dirt factor. HOD is a tube outside dirt factor. The difference between the reciprocal of dirty and clean overall heat transfer coefficient is determined by the term overall fouling resistance RF, such that RF equal to 1 by UD minus 1 by UC, RF equal to 1 by HOD plus DO by DI times 1 by HID. The effect of including the fouling factor in the overall heat transfer equation is to increase the heat transfer area of the heat exchanger so that the exchanger performance does not suffer due to fouling when the exchanger is in service. For example, let us consider a water-water heat exchanger. For this heat transfer service, the values of UD and RF are UD equal to 3000 watts per meter squared Kelvin, RF equal to 0.0001 meter squared Kelvin per watt. The values of capital UC is calculated from the expression for RF equal to 1 by capital UD minus 1 by capital UC. So UC works out to 4285 watt per meter squared Kelvin. For this service with same heat duty and LMTD, the area of the heat exchanger based on UD and UF are such that AD by AC equal to UC by UD, which is equal to 4285 divided by 3000, which works out to 1.42. Thus, the fouling resistances add about 42% additional area to the area required for a clean heat exchanger as depicted below. If the designer is conservative and not sure of the fouling behavior, particularly in heat recovery exchangers and process reactor train, oversizing is the most frequently used approach by assuming higher fouling resistance. But note, oversizing usually increases fouling, particularly at the startup, because the exchanger is clean and area is larger and velocity is lower. The values of fouling resistance selected for the exchanger design is somewhat arbitrary and is based on the designer's experience with the type of heat transfer service. TMO, the Tubular Exchanger Manufacturer Association, provides a table of experienced values of fouling factors for various units and fluids. These are simply the recommended values depending on the hot and cold fluids used for the initial design of the heat exchanger. You have no information with regard to how the fouling varies with the time and changes in flow rates. The fouling layer of deposit builds on the tube surface over a period of time. The design fouling factor relates to the fouling resistance expected in the exchanger after the expiry of certain time period of service. It is expected that exchanger will be able to deliver the design thermal performance till that time. At this point of time, the exchanger has to be taken for cleaning. Types of fouling. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. Fouling in general is classified into following categories: precipitation fouling, particulate fouling, chemical reaction fouling, corrosion fouling, biological fouling, and freeze fouling. Precipitation fouling. Precipitation fouling involves crystallization of dissolved salts onto the heat transfer surface due to changes in solubility. The precipitation of solute from a solution, such as water, containing dissolved salts occurs when it gets supersaturated due to evaporation or heating or cooling beyond the solubility limits. In a recirculating cooling water system, concentration of mineral ions in water continuously increases due to water evaporation. When the concentrated water is heated inside a heat transfer equipment, the calcium and bicarbonates ions precipitate due to the changes in solubility, forming hot scale on the heat transfer surfaces and clogging pipes and manifolds. Besides, deposited salts or scales on the heat transfer surfaces reduces the cross-sectional area of the flow passages. The flow rate of the coolant decreases and the pressure loss of the system increases. This process is called scaling. This figure shows the solubility characteristics of certain dissolved salts in water as the water temperature increases. This is an example of the dissolved salt exhibiting decrease in solubility as the temperature increases. As the temperature of the salt solution T1 increases along the saturation curve, precipitation fouling occurs. When the solubility exceeds that's corresponding to the saturation temperature Ts. This typically happens in coolers where cooling water is used as a utility. The cooling water contains salts such as calcium sulfate and calcium carbonates, etc., which has inverse solubility characteristics. Particulate fouling. Particulate fouling involves deposition of solids suspended in the gas or liquid stream on the tube surfaces. The suspended particles may originate from the cracking reactions of hydrocarbons in fired heaters or chemical reactors or corrosion of the fluid with piping material that carry the fluid to the heat transfer surfaces. Chemical reaction fouling. Chemical reaction fouling is caused by deposits formed by the chemical reaction within the process fluid. Typical example is the polymerization of certain components of the process stream at high temperature of the operation, which subsequently forms a layer of coating on the heat transfer surface. In corrosion fouling, the process fluid flowing through the heat transfer tubes reacts with the tube material and the products of corrosion reaction deposit on the tube surface. The process stream may have acidic components which causes the tube material to corrode. The corrosion fouling should be considered as a particulate fouling and prevented as a particulate fouling. Biological fouling. Biological fouling involves formation of film of living matter or microorganisms on the heat transfer surface. It is called biofouling. The microorganisms include algae, fungi, and bacteria. Algae are green in color. They need oxygen and sunlight to grow and therefore exist in cooling tower. Fungi are similar to algae but do not need sunlight. They require moisture and air and exist on the nutrients found in cooling water. Bacteria can live with or without oxygen. Water and other wet environments are suitable for bacterial growth. Heat exchangers therefore provide the conducive environment for the biological matter growth and fouling. Freeze fouling. Freeze fouling is the result of freezing of a liquid or a component of a fluid having high melting point in a multi-component mixer on a surface that is subcooled. Examples include freezing of water in heat transfer surfaces in air liquefaction plants, chilled water heat exchangers using glycol water, that is brine. Factors influencing fouling. Factors that influences the fouling on heat transfer surfaces include the operating conditions, fluid properties, design parameters of heat exchangers. First, the operating conditions. Fluid velocity. One of the most important operating parameters that affect the fouling tendency of the fluid is its velocity. As the fluid velocity increases, the rate of fouling decreases in several types of the fouling discussed earlier. High velocity or turbulent flow keeps the particles in suspension. and prevents particulate fouling. While an increase in velocity increases the rate of formation of fouling layer on the surface, it also increases the rate of removal of the deposits. Thus, the net rate of formation of fouling layer is decreased. Next, the temperature. Temperature of the fluid greatly influences the chemical reaction fouling. Higher the temperature, greater the reaction rate, and hence the rate of reaction fouling. Similarly, temperature also influences the precipitation fouling. Higher the temperature, greater the fouling rate in case of liquid with inverse solubility temperature relationship. Gas side fouling in the process fluid is predominantly due to formation of coke at high temperatures in fired heater furnaces and the deposition of the same on the tube surface in the downstream heat exchangers for heat recovery. Temperature plays an important role in determining the amount of coke formed and hence the rate of deposition on the heat exchanger tube surface. Two, fluid properties. Dissolved salts with inverse solubility temperature relationship will lead to precipitation fouling. Suspended particulate matter in the fluid stream will deposit on cold surfaces and cause particulate fouling. Examples include economizers in boiler system. Combustion products in boilers contain acid gases such as CO2 and SO2. These gases condenses when the temperature of the flue gas drops below the dew point in the heat recovery exchangers installed in the flue gas loop, causing corrosion fouling. Number 3. Exchanger design parameters. Fouling aspect is given due consideration in selection and design of heat exchangers. The design parameters have considerable impact on the fouling behavior of the heat transfer surfaces. Notable among them are type of heat exchanger and nature of the surface or the surface finish. Type of heat exchanger. Shell and tip heat exchangers are more prone to fouling than plate and frame heat exchangers. The reason being, in plate heat exchangers, the velocity is much higher and the fluid path is more tortuous and turbulent than that in the shell and tip heat exchangers. As the flow passes through the channels, it constantly changes its direction and velocity, thus ensuring turbulence even at very low flow rates. Nature of the surface or surface finish. Rough surface are known to promote fouling by collecting particulate matter. Thus, carbon steel is more prone to particulate fouling compared to stainless steel, which has smooth surface finish. Fouling mitigation. Having understood the impact of fouling and types of fouling, the next step is to discuss how fouling is mitigated in process industries. Fouling cannot be prevented by proper selection and sizing of heat exchangers. For sustained thermal performance during operation of the exchangers, fouling needs to be controlled by properly implemented treatment program wherever possible. The effective fouling mitigation strategies include selection and design of heat exchangers, appropriate treatment program during operation of the heat exchangers. Gas side fouling is different from liquid soil fouling. Hence, the two has to be treated and discussed separately. Fouling mitigation strategies for gas side fouling. There are hardly any established treatment programs which can be universally applied for gas side fouling mitigation. The origin of the gas side fouling is a heat generation source, such as fired heater or furnace or boiler, where the fuels are burnt. On the fire side of the boiler or fired heater, the carbonaceous matter or soot in the combustion products causes fouling. On the process side, the coke formed in the fired heater tubes at high temperatures with hydrocarbon as feed is a source of fouling in the heat exchangers in the heat recovery sections downstream. Hence, in most cases, the gas fouling is treated as a particulate fouling. The mitigation and prevention methods are those applicable to particulate fouling. In fired heaters, furnaces, and boilers, the fouling from combustion gases can occur in feed preheaters, economizers, and superheaters. Illustrated in this figure is a feed preheater installed in a fired heater. The composition of combustion products are dependent on the types of fuel burnt. Fossil fuels contain carbon, hydrogen, sulfur, and ash. The components of combustion gases include solids and gases that consist of the following: ash, CO2, SO2, CO, water, oxygen, and nitrogen. Ash accumulates on the heat recovery exchangers in furnaces and fired heaters and causes particulate fouling. CO2 and SO2 combine with water forms acid, which condenses when the gases are cooled below the dew point and causes corrosion fouling. Selection of fuel for the burner is an important design consideration from fouling point of view. Natural gas and fuel gases contain no ash and are considered clean, and their combustion products do not cause particulate fouling. However, corrosion fouling does occur, and operating above dew point is an important requirement as a mitigation measure. Fouling factors of typical fossil fuels are presented in the table. Fouling resistance RF is expressed in hour feet square degree Fahrenheit per BTU. Fuel oil 2.002, fuel oil 6.005, natural gas 0.0005 to 002, light hydrocarbon 0.001, naphtha 0.002. It is apparent that the clean fuels have lower fouling resistance and should be considered an alternative wherever possible as a mitigation measure. Fuel additives. Combustion of high ash oils in boilers produces troublesome deposits on boiler convection surfaces such as steam generation, superheater, and economizer. Fuel additives have been used successfully in boilers across industries to control the fouling. Fuel additives are intended to control fouling by forming friable, non-adherent deposits that can be removed by soot blowing. Other factors that can be considered for mitigation of gas side fouling are high efficiency burner, flue gas velocity, and excess air. This figure illustrates how a burner design and efficiency influences combustion products of fossil fuel in a fired heater. An efficient burner design will lead to negligible production of particulate matter, CO, and less NOx. Excess air is an important influencing factor for converting SO2 to SO3 by the oxidation reaction, which then combines with water in the flue gas to form sulfuric acid. Higher the concentration of sulfuric acid, the lower the dew point, and greater will be the corrosion fouling of the heat transfer surface. Fouling mitigation strategies, liquid soil fouling. Two important cases of liquid soil fouling in process industries are cooling water system and steam system. Cooling water system. In heat exchangers which use cooling water, the precipitation fouling is of major concern. Two types of scale are usually formed in water system: calcium carbonate scale, calcium sulfate scale. Calcium carbonate scale. Calcium carbonate scale is formed when calcium or bicarbonate alkalinity is present in water. An increase in temperature and or an increase in pH will cause calcium carbonate to precipitate according to the reaction below. Calcium bicarbonate gives rise to calcium carbonate, which is solid, carbon dioxide, which is gas, plus water. Calcium sulfate scale is much more soluble than calcium carbonate and hence will precipitate only after calcium carbonate scale has formed. Calcium carbonate precipitates faster as the temperature increases. Hence, limiting the temperature rise in heat transfer surface is one of the ways to limit the precipitation fouling. Design consideration include the following. 1. Use highest pressure drop as possible. This indirectly means high velocity. A high pressure drop implies higher shear stress. The shear stress work as descalers by constantly imposing forces on the deposited material that pull the particulate matter away from the surface. Design consideration 2. When the hot side fluid temperature is greater than 70 degrees centigrade and water on the cold side is scale forming in nature, pressure drops should be increased as much as possible on the water side, that is high velocity, and reduced on the hot side. This reduces the water temperature on the cooling water side. This makes scaling substance difficult to adhere to the surface. In process industries, the water side precipitation fouling is prevented or mitigated by water treatment programs. The formation of calcium carbonate can be controlled by adding acid, that is controlling pH at a recommended value, and adding water treatment chemicals such as organic polymers and polyacrylates. Calcium sulfate fouling can be prevented effectively by adding chemicals such as phosphate compounds or polyacrylates. The quality of cooling water and its nature and composition of the dissolved salts vary from one plant to another depending on the source of water. Thus, cooling water treatment program will vary from one plant to another. The treatment chemicals are specialty products and the service is offered by specialized water treatment companies, and the user needs to engage with them for appropriate treatment program. Particulate fouling mitigation. Particulate fouling is caused by suspended particles in the water such as mud and silt. The influencing factors discussed before such as fluid velocity and surface roughness are used to control the particulate fouling. It is usual to install side-stream filters in the water treatment plants to remove the suspended particles from the circulating water. The effectiveness of side-stream filters have been well proven and is useful strategy for particulate fouling mitigation in cooling water system. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of carry over into professional students. Thank you for watching.